Okay, so this is the CrackMe we're looking at. So you can go to here and find it. I'll put the link to it in the description so you can download it and have your own play around with it. But yeah, it's a quite nice one. It says difficulty 2.8. It's not the easiest one, it's not the hardest one, but it's got some nice, interesting things in it. And when I download this, run it. So I'm on Linux, so I'm just going to run it in Wine. You could run it on a virtual machine or Windows. So it's called this simple.exe. So when I run it, it just asks me here, it says enter key 9 chars length. So it's going to ask me to type something in, and then let's see what happens. So if I type, I don't know, let's try password 1. That's 9. And it says failed down here. So um, so we're going to be looking at how that works. We're going to reverse it and see how it works and see if we can crack the key. So this tutorial is in support of Rob Lawrie, who is a guy from Leeds in the UK who does a lot of work with children in refugee camps around Europe, France and Greece. And so he regularly makes trips down there with a van load of stuff that people have donated, so warm clothing, shoes, to protect their feet. Often they've got their shoes are in very poor condition. If they've got shoes, they've walked many miles. So it makes a big difference. And just to be a familiar face for them. So if you enjoyed this tutorial and you feel like doing something, then I'd appreciate if you send some money to this guy here. You can, if you go to his Facebook page, Rob Lawrie, I'll put the details in the video description, and you can just PayPal money to him, or just read and find about more what he's doing, and it might inspire you to help in your own way. But yeah, he's he's doing some great work. So just thank you very much. Right, I'm just going to load the binary into Ghidra so we can take a look, see how it works. So import file, it's this one here. Analyze it. Yep, and it's just some information here about the binary, so like how many bits, what architecture it's for. We'll close that. So when we start reversing something like this, it's a CrackMe, and the good thing about CrackMe is that they're often, you don't need to hunt around too much to find the code you're interested in. Whereas in a real situation where you're looking for a particular piece of functionality, you've got to do a lot of searching. But still, we need to find out where the code is that deals with the password that the user types in, so we can find out how to crack it to get the flag or the success message that we're trying to get. So we've loaded our code into Ghidra, and it's analyzed it. So the analysis does things like in the assembly, it looks for blocks of code, like where there are jumps from one area of code to another area of code, and it kind of identifies those as blocks. It looks for functions and things like that. So, where do we start? Usually the best place when we don't know where the interesting code is that we're looking for is to look in the strings to see if there's any strings we can recognize. Like we know there's a prompt that asks you to enter the password, so we could use that. In cases where sometimes you might find, like in a virus, for example, a piece of malware, you might find that there aren't plain text strings, so you can't easily search them in that way. They might be obfuscated in some way. And it might not be complicated, but it might not be obvious where those strings are used. So you might rely on functions in that case. So things like the binary will always include some libraries to do things. It might be lots of libraries, or it might just be a few of the core libraries that allow it to interact with the disk and the operating system. But we can look at which functions it imports, and we can see where those are used. So if we click on here, for example, we can look in different DLLs that this one's using. So stuff in there. This one is probably more interesting. So we can see things in here like functions like printf for printing to the console, and scanf. I saw just up there somewhere. There it is, just next to printf. So that's used for reading input from the user. So these are interesting places to look for references from the code. But we're going to go with the strings. So this CrackMe I chose this one because it's not so easy that you can just find the password hidden inside the binary and then type the right password in. But it's not too hard that it's, you have to spend a long time reversing it. But it's an interesting example, and it's got a few little interesting bits as well that I'll talk about later. So let's have a look what we're doing. So I've clicked on window here, and I'm looking for strings. So here, define strings. So these are all the strings that the analysis identified in the binary. And as soon as I've clicked on it, I can see some interesting ones here. Failed success. And also here you can see it says enter the key. So these are interesting. This is probably the code that I want to be at. So let's go for this one. So the prompt that lets me enter my key. So this is the address of that string in the binary. And so I'm going to jump to that. So if I click on it, in fact, it's appeared here now. So this shows where the string is in memory. You can see that it's next to lots of other strings because this isn't actually where the string is used. This is where it's defined in the binary. And so what I want to do now is get the address of where the string is defined, and I want to find references in the code to that one. So I just right click on it and I come down to references there. And then down here, there's a thing that says show references to address. So I click that. It searches and it's just given me one, which is good. So it's only used in one place. So this is pretty likely to be the place I want to look now. So I just click on that and I should find now that my code window, my assembly window, has jumped to the function that reference. In fact, there's the line. So there's a move to store that string at an address here in a local variable. We're gonna make sense of this more soon. And we can see that gets used, and then later on there's a call to printf, which is what prints out that message to enter the string. And then later on you can see there's a scanf. This is what reads the string from the user that the user types in, and then it does some stuff there. And I can see if I scroll down here, this is where the string success is used. It's printed to the screen. So it's when you start to identify things, it's good to start updating labels so that you remember what you're doing. So this one here is, in fact, if I look on the, this is quite a useful view. So we can look at that code, this assembly code. We're not going to look too much at assembly in this thing. We're going to look at the decompiler that Ghidra gives us, which helps here. But if I want to make more sense of this code, assembly, the code jumps around all over the place. So if you do it in a graph view like this, then I can see the different blocks within this function and what they're doing. And so there's two interesting ones that I'm going to label first, which are, because we're interested in reaching them, are this one that prints the failed string. So let's rename that one or edit the label. We'll call this failed. Just a little bit of doing these renaming things makes things a lot easier. This one is the exit. So everything that comes here then calls exit, which will exit the program. So if I click on that one and I edit the label, I'm going to call this one exit. Because the problem with assembly is that when you start looking at the code, it all looks the same until you start identifying, generally what things are doing. Then it all looks a bit confusing. What else have we got? So we've labeled failed, enabled exit, and somewhere there is a success one. Where's that one? In fact, if I go back to the code, I'll see it, I think. So failed or success, there it is. So this label I'm going to call success. So edit label, call it success. Good. So this is going to help me figure out what's going on. Right, we're not going to spend too long looking at the assembly here. We're going to use the nice thing about Ghidra is that it's got a really nice decompiler, which is what everybody raves about. They've really put a lot of time into making the decompiler help us. So we're going to look at this now. So I've closed my strings down, and now I'm on the decompiler window, and this is the function that I'm looking at in the decompiler. And you can see the nice thing is that it's got my labels here where they map to the decompiled code, like success, and you can't see the other ones because they don't really jump in the compiled code, but it doesn't matter. But it makes it easier to understand. Still a bit cryptic until we start exploring it in detail, but it's nice. The nice thing about the decompiler is that it doesn't the idea is not that you start with assembly and get a perfect decompiled version that then you can reverse easily. It's not the case. But the decompiler, sometimes it gets confused because it's basically working with code that could be quite greatly transformed by the compiler from the original code that somebody wrote in C or C++ into assembly language, and it can be difficult to get it back to how it was. Um, so the decompiler does a really good job, but it's not perfect. In this case, it does do a really good job, as we'll see. But you can see here, you can identify the main structures. But if you need to drill into certain things that look a bit strange in the decompiled version, then you can just by clicking on lines in here, it will take you to the code in assembly that it comes from. So it's really nice. Anyway, um, so let's have a look at this. First of all, what do we want to look at? Well, let's just start here. So we see the printf call here, which is really straightforward. So printf enter the key, 9 characters length. And then we see scanf, which, as I said before, is a function for reading strings from the user. Scanf, like printf, is to do with formatting output strings with dynamic user input. Scanf is the same, but in reverse. So it's like you can say if you want to read an integer from the user, so it's going to check that it's an integer, or if you want to read a string. And in this case, it restricts the length of the string that you can read to 9 characters. So that's good. So it reads the string from the user for the password that we've got to try and get correct to break this CrackMe. And then there's a few things going on down here. We can see, well, it's not entirely obvious what it's doing yet, but we can see failed down here. We can see success here. So we want to be up here to crack it. We don't want to be down there, and we don't know exit. We want to get success. So that's what we want. So let's start by trying to make sense of this code. Now, the first thing we can do that's going to be useful is this scanf here is, so the way scanf works is you pass it the address of a string variable or a character array. And when a user presses enter on the console, the data they typed in from the console gets stored into this character buffer. So the interesting thing we know from that is that scanf is expecting a character array here. If you look in the information about how scanf works, you can find that out. So let's rename this then to the input password or password input. Doesn't matter what you call it as long as you know what it means. So I'm going to take this local 19 variable and I'm going to rename it as input password. Good. And then the nice thing is I can see all over the code now, it all updates. So it's really nice. I can see it's much easier for me to see where that's getting passed around. Now there's one thing that we can look at here. So the decompiler doesn't really know what everything's doing. It didn't know that this was a character string. So input password at the moment, it thinks it's a single byte, but we know that it's reading 9 characters from the user and storing them somewhere. So it must not be just 1 byte. It must be an array of characters or bytes. It's just a character is like for printing, for example, but it's a byte. It's 1 byte. So let's update the data types to show that. So if we look on here, it's a bit clearer. So you see now I've renamed this to input password. This is the kind of the variables on the stack that the analysis has figured out. So when I clicked analyze at the start when I imported the binary, it figured out how the stack was being created in the function. So an area where we can have local variables, and there are these ones here that are being referenced in the code. But what we know now is that this input password isn't just 1 byte. It's probably going to be 10. I think it's an array of 10 because we're reading 9 characters from the user, and there's always that terminating 0 on the end of a string in C that we have. So it's going to be 10 characters. So what I can do now is take this type here that's on here, and I can say set data type. First of all, I'm going to set the type from byte to char. And I'll see when I do that a few little things. You can see now it's saying input password here equals /0. It's in the decompiler. It's recognizing it as a character now rather than just a byte check, which doesn't really matter in terms of how the code works, but it makes it easier to see what's going on in this view. But it's not just one char here. These will all merge together into one character array. So I'm going to do that now. So if I right click on here again and then set data type, and then I can say array, it's going to be array. It's saying 25. I don't think it's 25. If you look at the stack, it's going to be 10. So here, when you do that, it's saying when you change the size of this one stack variable that it identified in analysis to say it's an array of 10, it's going to clobber over these other ones. Is that okay? Well, that's okay because I've looked at, I can see the code here and I can see that it's using scanf and scanf is expecting an array of char. So I'm going to click yes. And I'll see now it's folded that into one local variable now of a char array of 10. And you can see my code now here that it's updated this, which is really nice. So what to do next? Let's follow this down. You can also see now that this scanf call is now referencing the array as a string, just showing it like it's using a string, which is good. So what's it do next? Well, scanf returns a value. The value that scanf returns, if I remember rightly, is how many things it parsed. So we wouldn't expect this to return 0. It might be possible to coerce it to return 0, but we're probably not going to expect that. So it's saying here, if it doesn't return 0, so if it did read something from the user, then it goes into this piece of code here. If it didn't, then if we just see where that bracket goes, if it didn't read anything in, then it just goes to exit. So we don't pass the CrackMe. We basically fail. So we come into here, and the first thing it says here is if the character, the first character in the input password is 0, so empty, go to success. We'll look at that afterwards. We won't worry about that now, but we've also got a jump point here, success, so we can see that it gets jumped to from down here as well, a condition down here. So we're going to look at this now. So what does it do? So after this check, we see here it does something with the input password. So it takes character 0, so the first character that the user typed in as a password, and it does a modulus with an hexadecimal F0, and it stores it in here. And then it does this check. And this if statement here, if this check fails, then we end up we fail the CrackMe. If we get through here, then we do some other stuff. So we know we want to get past this check. So what's it doing here? It's saying input password 0 plus this thing that it created here, this variable that was this modulus of F0. If it then adds the character to that thing that it just did, and it does a modulus of FF, and the result of doing that is hexadecimal 92, then we progress into the rest of the checks. So we need to pass that test first. So the first character must pass that test. What it's doing is it's kind of, when it's using modulus like this, it's kind of almost like doing a hash. So it's taking a plain text character and it's changing it in some way. And then it's expecting it to equal the value that's predefined in this code. So it's kind of a hash. And then if we if we look further down in this code now, once it's got the first character, then it sets this thing here to 0. Okay, IVAR equals 0. We can see there's a loop going on here, and it looks like this is some sort of counter of the loop. Okay, so and I can see down here that IVAR 3. It's confusing because they've all got similar names, but that's why when we rename them, it looks a bit more human user friendly. So it increments that at the end of the loop. So this is definitely some sort of loop counter. So I'm going to rename this now. So if I click on that thing, yeah, one thing when I rename variables like this, I noticed that this variable, is actually using it's stored in a CPU register, so EBX. And if there's a variable identified in the C decompiled C code, but that's actually come from a register, then I'll see when I change this to do, when I rename it, it'll change the name of other ones. I'll show you what that means. So if I change this to I, that's good. So now I've got this I value, but you can see up here it's changed this stuff because it was using that register as well. So what I do to make it clearer, it doesn't really matter, but when I do that, I'm going to say it's I. But I'm just going to say it comes from EBX. just so I know that I might see that I in other places where it's not being used as the same variable, but it's using the same register. Anyway, so I is 0. And then we can see, because we've got this index now, we can see what it's doing here. So at the start of this loop, it's saying bvar1 is equal to input password that the user typed in, this index in my loop, plus 1. So the index is going to be 0 to start with. So this is going to be the next character in the user input password. Because remember, we checked character 0 to start with, and now this is going to be the next one. So it's going to be input password 1 for the first time around the loop. And so this must be a character that it's reading out of there. So let's change this type. So bvar1 is the input password char. So it's a character, next character in the list. Good. So now it's starting to look a bit easier. And also we know that it's a character, because this is input password is a character array. So I'm going to also change the type. Where can I do that? Up here. Char, this one. Set data type char. Good. So it's starting to look a bit more manageable now. So we get the next character in the string that the user typed in, and here it's saying if that character is equal to 0, so a null, if it's the end of the string, so if it's been checking the characters are right using this hashing thing that we're looking at now, and it gets to the end of the user input string without creating a failure in the check, then it jumps up to success and it prints success and it returns. Okay, so that's how this loop breaks out, it seems. And then we've got this part here. So what's this doing? What this is doing is there's lots of conversion here, from a byte to an integer, and then to a long as well. This has probably come from this division, but all it means really here is that it's taking this character that we've just input, and it's doing this modulus, so it's dividing and then taking the remainder using this thing here. So f0 minus, and then it's this index, this loop index plus 1. So for the first one, when I is 0 to start with, this will just be 1, so it'll be f0 minus 1. And then for the next iteration, it will be f0 minus 2. So it looks like it's doing some hashing on each character, and it changes the hash slightly, so by 1 each time. And it also, we see it's adding this here. There's a, you see this value here, uvar, it's the same value here, and it's every time around the loop, it's altering that value that it's then using for the next character. So this is kind of like, I'll call it a stream key. It's like a key that they use to hash the characters, where they change it each time. So we'll call it a stream key. It's like, okay, what type is that? Just an integer, unsigned integer. So let's have a look if it makes it clear now. So stream key on for the first character, we do the modulus f0, and for every other character after that, we do a modulus with f0 minus the index of the character in the password. So it's the same thing really as the start, and whether it was written as separate checks, or whether it was the compiler generated it that way, and now it's been decompiled so that there's 2 separate checks, I don't know, but it's doing the same thing. So stream key. So we go around the loop, we do this thing to it where we're creating this, we're updating this stream key, and then there's this thing here, ivar1, which is also the same as this. This is, we increment I at the end of each loop, so ready to process the next character in user input. And this one, before we do that, this one gets set also to the current index plus 1. So I'm just going to rename this one as I plus 1, just so we know what that is. And so then we've got the condition in the loop. So you probably wouldn't write the code like this with a do while loop, but this is how it's been decompiled and generated by the compiler. But it's doing this, so it's saying we keep going around the loop we keep reading the characters, as long as the input password, so the next character that we're looking at, plus the stream key, so this thing that we're updating as we go around it, that we're hashing it against, hashed by FF equals, and then there's this thing down here, so I plus 1 local 22. So what's local 22? Well, we know that they're looking for, they seem to be hashing our input password, and they're looking to see if it matches something they expect already. And you can see here local 22. If I look up here, there's these things here that we've not really looked at yet, where it seems that some constant values have been set in the code to these things. Let's see what they are. You can see here that it's when it's referencing that, it's taking the address of this and then it's doing I plus 1. And so for each time around the loop, it's adding 1 byte to it's looking at the next byte in this local 22 thing. So this looks like, sorry, this looks like this is our password hash that we're checking against. So let's rename this. So local 22, rename variable. I'm going to call it password hash. Good. And if we just look at how that is in the stack up here, so password hash here, you can see these other things here, local 1E, local 1A, these things that also have those bytes hard-coded in them. And I know that it's expecting 9 characters in the user password because it tells us there, and we can see that it's checking for those 9 characters. And so the password hash, it looks like if you look at these, where it starts referencing this password hash variable, it says it's currently got analyzed as being 4 bytes, and then there's another 4 bytes, and then there's 1 byte. So altogether, there's 9 bytes there. So this and the way it's being referenced, and the way this loop is going round for each character until it reaches the end of the 9th character that was typed in by the user, it looks like this is going to be an array, a byte array of 9 long. Okay, so it doesn't need the 10 because it's not actually represented as a string. It doesn't need a terminating 0. They're literally checking each byte in it through this list. So we're going to update the type of this. We're going to say, first of all, we'll change the type to set data type to a byte. We're not going to say it's a char just because it's not really used as a character. It's used as a byte. So then we're going to say, well, it's not 1 byte long, the password hash. If you look at these, it's actually 9 bytes long. So set data type, we're going to turn it into an array. And actually, look here, it's actually recommended 9. Maybe the analysis picked it up, how long it is. Anyway, so we'll go with that. Yep, 9 looks good. Yep. So now look how our code is getting clearer. So now we've got a byte array of password hash 9, got our input password, got the next character that's being referenced in the loop, we've got our stream key, and so we can see here that this this password hash, look, it's the way it's setting them up now. This is actually an array, but the way it's been created is by setting these values here. But this is a start of password hash, the first 4 bytes. This is the next 4 bytes, and this is the 9th byte. This is because it's little endian. When it displays this string here, this value here, this means that the first byte is actually 92 hexadecimal. The second one is 89. We can see that if we look in the actual instruction that sets that value. We can see here the first byte there for this part is 92, 89, 2C, and A5. So that's our password hash. That's good. So we've got enough here to start to kind of write out some pseudocode of what's going on just to make it a bit clearer, and then to hopefully crack it. So yeah, first of all, what we're going to do is get this password hash. So this is going to be the characters 92, 89, 2C, A5, 7, 8. So let's put that into our code. Interestingly as well, the first index of this password hash isn't actually referenced because down here when it checks the password hash, it just checks I plus 1, so it's going to be the kind of second byte, so byte 1, not byte 0. So 92 doesn't get a reference, but we see that the first check here, which is probably no coincidence, is checking the first character, 0 of the input, and seeing if that hashes to give 92. So I don't know whether that was done by the compiler maybe, or whether it's just done like that, but the key is all here. So we're going to grab that now. Okay, so this is I've just created a little function with a link to which CrackMe this is. I've just written this out, so I've got the password hash here. So it's 9 bytes long. The first byte is 92, then 89, 2C, A5. Sorry, yeah, it's 9 bytes. 1, 2, 3, 4, 5, 6, 7, 8, 9. And these are all just copied from these bytes here. Okay, so let's have a go at writing the pseudocode for this function. So what does it do? Well, we're going to try and fold this up together. So we're going to say it creates this stream key thing, and it does it for the first byte. It does a modulus of F0, and then it does it for the next byte. It does it with a modulus of F0 minus the index of the next character. So it will go -1, -2, -3, -4. So we're going to create a loop for each character, and then we keep building up that stream key, and then we do this thing to do the actual check against a hash. Yep. So the first thing we do is, let's just copy this code, make it a bit saner. So, and then here's the check. Right, okay, that's what we've got. So let's try and make that into some sense. So I'm going to say that the stream key, because I'm going to do it all in kind of one loop rather than a separate check for the first character, equals, because like in here we've got there's a first check to check if the first one hashes to 92 for the first character, then it goes into the loop, and then it does it for each of the other characters. But we can see that it's doing the same thing. So if I say stream key equals 0, I'll turn this into Python code, and then we can crack it. So stream key equals 0, and then what it does is it goes for each input char in user, what do we call it, input password, so the password typed by the user. We're going to take each character, and then we're going to update this stream key thing. So we'll copy that. We're going to say the stream key equals the input password. It's actually stream, because we're putting it all into one loop, stream key plus, because it gets added each time. We'll start it at 0. That's why I put it at 0, because this one will first be 0 for the first character. And then we add input passwords, and it's not, we're going to take this from input char. So we're looping through it, and we do a modulus of F0. because we change this each time, we need to get the index of the character in the password. So I'm starting to write Python code now, but just kind of loosely, so I know what I'm doing. So for each input character, we take the stream key and we add to it the current input character that we're looking at. We do a modulus of F0 minus I, so minus the index of the character that we're checking. Yep. And that updates the stream key for the next check that we're going to do, which is this. We're going to say if this condition now matches, then it means that the input character is correct. So let's just write that. So we say if the input char plus the stream key, so I'm just copying this stuff down here now. I'm just turning that into sort of Python-like code. If input char plus the stream key, so the current value of stream key, all modulus this thing. Okay, I'll put brackets around here just to make it clear, equals the password hash. So remember, we grabbed it into here. So if it equals the password hash of the current index. Yeah. Now, it might be confusing at first because this is I plus 1, but remember in the loop in the code starts the index as 0, and it always references the character as I plus 1. So the next character in the loop, it's already checked the first one, that's why. But we're folding it into one loop so that we're going through each character. So what I forgot. If input character plus the stream key modulus ff equals the password hash at the index. So for the first one, we saw that it's going to be 92 that it's checking. The next one, it's going to be 89. So 92, 89, 2C coming from here. And if that matches, then we say print success. Actually, we won't print success. We're going to print the character. Okay, so print password, call it password index equals so print password I, and then the character that we found in the input. Okay, let's just have a look at that. Just put this stuff down here. I'm going to get rid of that soon. So let's just check this. So we have the stream key. We start it as 0 because the first time round we add to this stream key, we add the input char modulus f0 minus I, and remember that I is going to be 0 to start with for the first characters. This will just be modulus f0, which relates to this code here. Okay, and then it gets the stream key and it adds that stream key value to the current input char. So that's down here. Oh no, sorry. That is down here. So it adds the stream key to the input char, modulus it by ff, and then checks it against the password hash, which is, so yes, it's saying input char, add the stream key, and then modulus ff equals the password hash, and then we print out the password. Right. That's the algorithm as it appears in the code. But what we want to do is crack that password. So to do that, we just need to turn this into like a bit of a cracking script. So yeah, first I'm going to create an array called cracked key equals, and we're going to add as we crack the password, we're going to add it onto there. So what do we want to do? Well, so when we're cracking the password, we don't know what the characters are that when they get transformed, they match the expected hash values. So what we need to do is to try each character. So brute force like the first character, and when we found the first character, then we can carry on and brute force the next character. And we just go through until we've done them all of them. So what that means is that we just need to, so for each password hash byte in here, we're going to loop through these, and we're going to try and find an input plain text character that leads to that when it goes through this transformation that we've just described here. So we're going to start by iterating through these. So if we go for password hash char in password hash, it's going to loop through each character. But we also need to keep track of the index because the index is important for when we're doing the hash. So the index is which character we're looking at in the password hash. So 0, 1, 2, 3. So we're going to make sure we get that too. So we use enumerate like this. Good. So for each of the password hash charts, we want to find the text input that was going to allow us to crack that to match the hash. So now what I'm going to do is say call it candidate char, because we don't know if it's the right one yet, but we're going to loop through it. For candidate char in, if I import string in here, for candidate char in string dot printable, which in Python in this string module, printable is the set of all printable characters. So we're going to try those. We're going to just loop through them. But basically we want to loop through every character like ASCII character, like 0 to 255. Right, so one thing we need to keep track of when we're going through here is that the stream key. So if I'm going to set the stream key equal to 0 to start with, and then for each one of these things, now it's tempting to just say stream key. In fact, we can copy our pseudocode because it's pretty much Python, I think. So stream key equals stream key plus input char. We called it candidate char. Candidate char modulus f0 minus I. Stream key equals stream key plus that. And then we are going to, yep, that's good. So we've got the stream key, and then we're going to do the comparison to see if this is the right character or not. So we're going to copy this code down here. So if input char, we called it candidate char, just to remind us that we don't know if it's the right one yet. So candidate char plus the stream key modulus ff equals password hash I. That looks all right. Then we should be able to print out that should be candidate char password, and we should be able to say cracked key append candidate char and break out of this one because we don't need to look at any more characters. We've got a match. Right, I'm just going to add, just put this in. This will print out the password hash that we're trying to aim for. And okay, so let's have a look. I'm just going to run this. It's not quite ready yet, but we'll see when I run it what's going to happen. Yeah, you can see here complaining about strings. So what I need to do is when I'm doing these candidate char things, I'm actually computing them against numbers, numerics. So really I should be saying not the character, but the order of the character. So the byte, like the value, the integer representation of that character. So I need to do that for these. So I say ord. Is that all of them? That's fine, that one. And then that's fine. So I just had to use ord there. Let's try this. See what happens. Ah, good. But I mentioned that it wasn't quite ready yet because if I go back to this thing here, in my example here, when I was creating this stream key thing, the algorithm is assuming that it's running through the right password that's been input by the user. So every time it goes through the loop and updates the stream key, it's expecting it's got the right key or it's not got the right key, whereas we're trying to brute force the key. And so what I'm doing here, there's a little mistake here because for each candidate character in a string, I'm updating the stream key, and I might crack one of those characters and then I go on to the next one. But for all the wrong candidate characters that I'm also using, I'm updating the stream key. So what I need to do here is not update the stream key at this point, but only update the stream key when I've found it is the correct character, so that when it goes on to the next character, the stream key is correct for that next one. Okay, so all I need to do for that is to change this so that it's a different variable. I'm going to call it underscore stream key. Or I could call it, let's call it candidate stream key. So it's even more clear. So it means it will, if we find this character, it will become the next stream key. And if we match one, then we store that that character that we cracked, but then we also update our kind of global stream key to become the candidate, the one that we found matched the right character. So let's try this. And let's just, let's try this. Haha, boom. So this is what it's found that matches the algorithm. This password hash, it's found plain text characters, first character I space am space back, I am back. That's nice. So let's just print it out at the end here. So we're going to say print cracked key, or password, whatever you want to call it, cracked password, and then we're going to do join cracked key. Spell that correctly. Let's just clear the screen for demo effect. A cracked password, I am back. Right, let's just check this in the actual CrackMe. So I'm going to run the CrackMe, enter key. So let's try it. I am back. Boom. Cracked it. That's good. But there's something else in here. I mentioned a little bit earlier, sorry. I mentioned earlier that there was some interesting stuff, and one interesting thing about this here, if you look at it carefully, this loop here, is that as we go through the characters and we validate one character and then we go on to validate the next character, and then it stops and goes to success after it reaches the end of the user input. So if you look here, so let's just walk through it. So the first character matches, which we found to be I, matches 92, so I, and then it goes into this loop and it gets the next character. But if that next character equals the empty string, then it says go to success. And so according to this algorithm, what that means is that if we just put one character in that's correct, then it will also go to success. Let's try that. Which is it looks like a little, maybe either an Easter egg or a little bug in the CrackMe. So let's try that. So it should just let us, as long as any character is correct until it gets to the end of the string, then it should report success. Let's just try that. So if I run it again and I type I, enter, success. And also if I do I space am, sorry, I need to run the actual program. So wine, so if I try I space am, success. So basically it doesn't check that I'm entering the full password, so I just need to check enter the first one. But anyway, regardless, it's an interesting CrackMe, and there you go. So yeah, so what helped us there? Well, it was so what did we do? To recap, we went to find the bit of the interesting part of the code. Sometimes you can have tons and tons of stuff that you don't really need to see when you might be interested in a vulnerability, you might be interested in a particular feature like a network protocol, how it gets parsed and stuff like that. So you want to focus in on that area that you're going to reverse, and once you found that, you start focusing your attention onto that area. And so what we did was we found the function. In fact, we can call this function, can we rename it here? Rename function, we'll call it main app, just so that if we come back to look at this code later, we can do. And then we started to, what did we do? So we recognized that the user input was coming into the scanf function. So we renamed this variable as input password, and we recognized that it was a character array. When we looked at the stack up here, we saw that there was space on there for 10 characters. So we helped the decompiler help to clear it up by saying that's character array. So it reads the stuff into there. And then we start going into this main algorithm, and when we put we identified that there was this stream key thing that was going on that was being updated for every character here and here at the start. And then we also recognized that it was checking down here. We could see that it was checking that hashed value of each character against this thing here, which we recognized as being a kind of password hash that was stored in the hard coded into it. So it's set up like this, which we identified as being a byte array. Where's it gone? Up here. This thing here, and it was 9 characters long. We could see that from the way the stack was laid out. that there was space for 9 bytes on there. And the way it was indexing those in here helped us to identify that. And so as we started to identify the types of things, it helped us to reverse the rest of it. You don't always have to understand exactly how it's working. You look at it and you might see like some of this stuff looks a bit strange in the decompiler, but you kind of get the gist for how it's working, and then you can start trying stuff, writing a bit of pseudocode or writing some Python code, and trying a few things out and seeing what happens. And then it starts to become a bit clearer. But yeah, so there we go. I hope that was interesting, and yeah,